We are asked to solve this problem using a logarithm. So let's take a moment to read. This medication, which I can't pronounce, is used to treat asthma. It has a half-life of 3.4 hours in children age 1 through 4. A child is given a dose of 400 milligrams once a day. How long does it take until the child has only 25 milligrams remaining in their system? This was a challenging problem. First off, it does not give us a formula to work with. Secondly, it does not give us a percentage per hour that the medication is changing by. Instead, it gives us the half-life. So I'm going to associate half-life with exponential. So just trying to illuminate my thoughts here. Half-life goes with exponential, which means that I want to write an NPAT formula. Which means that I need to figure out time. And so this is hours, so I need a decay factor because of the half-life is the idea that it is decreasing. So I need a decay factor for 1 hour. So we started off by making a little chart to help us do that. So we wrote down the A and we wrote down the corresponding time. And so in this problem, they give me half. Half-life I know is the decimal point, 5 or 50% is missing. And the time for that is 3.4 hours. So I know that 1 hour would equal 1 over 3.4 as much time. As long, I guess I should put in there as sort of the label. So because it is a shorter time, I'm going to take the 0.5 with the exponent of 1 over 3.4 to try to get that to the length of time of 1 hour so that when I solve, I'll have an answer in hours. So I'm going to my calculator, putting in 0.5 for the half, the 50%, to the, and then making sure if I have an ordered calculator that I'm using parentheses to type 1 divided by 3.4 as the exponent. And so on my calculator, this equals 0.8155, 7, etc. We're going to round to 3 decimal places, so 0.816. So there's my A. Now in NPAT, I know that the P is the starting amount. So N equals, the child was given 400. The A value is 0.816, and T is time. So there's my NPAT formula. Now I'm asked how long, so I know that I'm solving for the time, until the child has only 25 milligrams. So that 25 milligrams is going to go in for N because that is a number of items. So 25, 400, 0.816 to the T power. And then I could solve this by graphing, but I am told to solve with a logarithm. So I am going to solve it out by hand and show all of my work for that, show the use of a logarithm. The steps are very much the same for all of these problems once we have them set up. So step 1 is to divide by the start. And that is to isolate the base and the exponent. So I'm going to divide by 400 on both sides. And that's always the way I start these problems. It's just getting rid of that number, making it as simplified as I possibly can. So 25 divided by 400 gives me 0.0625. And that's equal to 0.816 to the T power. Now, I know that the inverse of an exponent is a logarithm. So my step 2 is to use log on both sides. I know I have to do the same thing to both sides. So I'm going to, on the left, put log, and then I'm putting my parentheses, 0.0625. And I have to do the same thing on the right, so I put log, my parentheses, the 0.816 is in the inside, the t is the exponent. Now, my third step here is to use power property. The power property is when you have the exponents inside and outside the parentheses, and we know that a logarithm is equivalent to an exponent, so that's why the 0.816 is acting like an exponent. We also said that the way that we write this is to move the exponent to the front so that we know that it's outside the parentheses. So I'm going to take this exponent t, I'm going to move it to the front right here. Okay? So this is really the key step. If we get this step right, it's going to work out for us. So now I have log, parenthesis, 0.0625 equals t times the log of 0.816. And then my final step is to divide. So I want to get t by itself. It's multiplied because of the power property. And so I'm going to divide on both sides by the log of 0.816. On the right-hand side, these guys cancel. So that's just t. That's what I was asked to figure out. And on the left-hand side, I do want to be careful with typing this. So I'm going to type log, the LOG button, 0.0625, end parentheses, and then divide by log of 0.816, and then end parentheses with that one. And when I do that, I get 13.6 hours. And so that's my answer. I figured out the time. In 13 hours, they're down to 25. Now, in this problem, I want to show us an extra step because we're here on the video, and so if you don't want to see it, you don't have to, but it's kind of cool. So if I make a chart where it's the time versus the milligrams. So we start off at time is 0, milligrams of 400, because that's what the starting dose was. And then it told us in the problem that if we go 3.4 hours, excuse me one moment, sorry about that, that it will be half as much. So in 3.4 hours, it should be down to 200 milligrams. And then that idea of half-life means that if I would go another 3.4 hours, so then I'd be up to 6.8 hours, it would be half again, so it would be 100. And if I go another 3.4 hours, so if I add here plus 3.4, showing the half-life, I would be up to 10.2 hours. And I would have half as much, so 50, because half-life is a constant, so every time. Again, if I would go another 3.4 hours, I would be up to 13.6. And I would go half as much, which is 25. And this last pair, right down here, is actually the pair that we solved for over here. So when we created this formula, instead of having the table, and then we did the algebra over here, and we got the 13.6 hours, which matches the 10 in the table. So I just felt like that was a really cool way to double check. That does not always work out with every problem because they don't always give you amounts that you could find by exactly dividing in half. So in this one, if they had asked us about 20 milligrams, we would not have been able to solve it with the table. But because 25 is one of those numbers we can get by dividing by half and dividing by half again and again. This one we could solve with the